Bismillahirrahmanirrahim. Welcome to the second lecture of multimedia technology and application. So today we are going to study about classes of multimedia applications. So what is the classes of multimedia applications? So you know about a multimedia: audio, video, streaming, live streaming, images, compression of a video, audio, etc. So these things called classes of multimedia. Classes of multimedia application is the first one is streaming, store audio and video, streaming live audio and video. This one is store one, like you copied the data or you store the video or audio in somewhere in a computer memory, then sometime you want to be watch it out, you can. And you want streaming live, so like in a Google you also live streaming cricket, live streaming whatever you want live, so it's called live audio and video. And the third is a real-time interactive audio and video. We will see this as well, and some other concept of multimedia application as well. So the first one is class streaming, store audio and video. So streaming, store audio and video, it means you already have the storage data, and it will be in the form of audio, it will be in the form of video. So the first characteristic is the multimedia content has been pre-recorded and stored on a server. Again the same, already you have a video of recorded, you have audio of recorded, and it's already stored in a server, maybe in your memory. So whenever you want to watch it out, you can. So user may pause, may rewind, may forward, because is it in your hand, you can do forward, rewind, pause, close, whatever, because it's already stored in your memory. So the third is the time between the initial request and display start can be 1 to 10 seconds. It's just like whenever you want to play the audio or video, so it just a little bit takes a time. In 1 second you just click it out. When you double click on a audio or a video, it just take initially just like 1 second, 2 second, 3 second. So when the file is when the file is not a lot, so it can play easily, but when a file is too long, have a lot of space, so when you are playing the video or long video, so it takes a time when it's going to be start. The thing is constraint. After display start, the playout must be continued. It means the data, the movie or the audio will be stored continuously, like 1 second, 2 second, 3, 4, 5 second, 1 minute, 1.5, and so on, like a movie. When you are going to play the movie, play the music, play the song, so the song or movie, whatever, it's going to be continued. It's not be like that you're watching on a 1 minute, then it by automatic is jump to the point of 30 minutes. It's not, it means like continuous 1 second, 2 second, 3 second, 1 minute, 2 minutes, 3 minutes, just like that. So this is the thing is streaming, store audio and video. So the data which already stored and it is in your hand, whatever you want to do with the audio or video, you can do that. Now the second characteristic, now class streaming live audio and video. We studied streaming stored, now streaming live. So streaming live is just like similarly like broadcasting. You are watching a news on a television or a radio or internet maybe. So this is called live streaming. Sometime you are going to watch a live cricket match on internet. You have to streaming live cricket match, Afghanistan versus Australia, like that. So similar like a broadcast television or radio. It is non-interactive Non-interactive mean you cannot forward it, you cannot pause, you cannot rewind, you just view, you just watch it, and you just listen it whatever the broadcast channel is going to show you. So it is not in your hand. The first one was in your hand, you can rewind, you can pause, whatever you want to do that. You were doing that with the first one, like a streaming store. In a streaming lab, you cannot do anything with the audio or a video, like you cannot pause, rewind, often combined with the multicast just like you have a cable connection, and the cable connections is coming to your home, and you have a connector there, and you can take connection from a connector to one room, another room, third room, and you can watch it in a multiple room on multiple television. So it's called multicast. The time between the initial request and display can be up to 10 seconds. What does it mean? Whenever you are going to open or on the channel on the television, and the screen is coming in front of you, so it takes a time. So that's called initial request and display start time, so which is equal to up to 10 seconds. The third is constraint. What is constraint again? Like a store streaming, after display start, the playout must be continuous. Again continuous. The previous one was also by continuous. It's also be because it's audio, it's a video which is streaming live from one of the broadcaster, so that will be continuous. And which is not going to be like it the video or the audio cannot be jumped, cannot be flipped from 1 second to directly to the second 50 or minutes 10. It not be like that, so it will be continuous. Now the third was real time interactive audio and video. So in real time now, it's just like a phone conversation or a video conference call. Whenever you are making a video call or you are making a phone call, so a phone call or video conference which have initial delay time, and we always want a minimum delay time whenever you are going to call or when you are making a phone call with someone. So real-time interactive audio videos like phone conversation or video conference constraint would be like a delay between initial request and display start must be small. Why it will be small? Because whenever you are talking with someone and there is a big delay, so you are talking like hello. So when the delay is large and you are talking like hello, how are you, fine, what are you doing, so you're talking a lot, and there is a delay like from a sender to receiver, and there is a delay, like you can see point A is a sender, B is a receiver, so you are communicating with A to B. So when this delay is large, so some of your bit will be lost because you are continuously talking and there is a delay. So due to delay, your talking is going to be, your bits is going to be lost. Once the delay is going to be reduced when there is a small delay between the communication, so your bit will be transferred from point A to point B with a minimum delay, and so a minimum data will be lost, minimum bit will be lost. So that's why we are saying in the real-time interactive audio and video we need a small delay. So like you are watching a video now, like you are making a conference call, when there is a lot of a delay, so the video is going to be buffer, just scrolling, then scrolling, because there is a lot of a delay. When there's a small delay, so the video will not be scrolling, and you are watching a video call like a movie, like you are watching a movie. There's no buffering, browsing like that. So for a video, the delay must be less than 150 millisecond, which is acceptable. For audio, 150 millisecond not perceived, but less than 400 millisecond also be acceptable. So why video is 150 and audio is like 400? Because in a video we have a graphics, so in a graphic have a lot of views, so that's why we need a minimum delay for a video. In audio we just have a voice, in a voice we just have a bit, so the delay between audio and video is comparable, so the delay of video is lesser than audio. Again, constraint, the playout must be continuous, because you are continuously talking with someone and your phone call is you are communicating with someone. So coming to the fourth one, other class. So the other including multimedia sharing application. We have a lot of sharing application, download and then played application, example App Store, Unit Lab, Freenet, etc. Also distance learning application, like we are doing online classes or making a video then uploading on Summit, just like a distance learning application. Coordinate video, audio and data, typically distributed on a CD, because you have a movie and you want to be uploaded in the shape of a CD, and your CD or DVD like that. So it's the other class of multimedia. So other thing we will be studied, so the outline we will be studied later on. Classes of multimedia application, which we studied a little bit. Requirement and constraint of the multimedia application. Problem with today internet and solution. Common multimedia protocol. So common multimedia protocol is RTP and RTCP. And the last one is accessing multimedia data through a web server. So what kind of a challenging we will face? So the first challenge is like TCP UDP IP should provide best effort. It means, what is TCP UDP IP? You know about that. TCP is transmission protocol, UDP also a datagram protocol, and IP protocol line. So you cannot guarantee to someone that how much delay will be there, because it's a wireless network, maybe it's a landline, but there is always a delay. So one challenge in a multimedia is delay or packet delay of the communication. The second challenge is second challenge is performance deteriorate if link or congested. It's another one challenge when a lot of people are talking on a single channel, so the channel or the link is going to be congested. Congested means a lot of people is talking, or you have a one ball, a lot of people are playing with the one ball, so the ball is going to be congested, nobody can receive the ball. So this called congestion is another challenging for us as well in multimedia when the link is congested. Another challenge is most router implemented use only first come and first out server. So we have a router, a lot of different kind of router we have. So a lot of routers work first come first server. So it just like, so again it's another challenging as well. So now we have some kind of problem and solution for that as well for a multimedia. So the first, coming to this one, limited bandwidth. Whenever you have a limited bandwidth, so limited means like you have a 2 MB bandwidth, and you know about the MB bandwidth. So and you're like you have a video of a 10 MB and your bandwidth is 8 MB. So all whole of your video is not coming in the 8 MB now, because your video is 10 MB and your bandwidth is 8 MB. So what you are going to do, you are going to compress your video. So it's one solution. So the another problem is packet jitter. So whenever you are facing a packet jitter, for that what you are going to do, you are going to do play out delay for a audio. So what kind of, like you can see voice over IP phone. You are assigning a IP and the phone is going to work on the internet base or IP base. It's another one. The other is packet loss. So packet loss, whenever you are assigning a data, whenever you are transferring a data from A to B, you are transferring a data from A to B, but sometime the link is going to be disturbed. This link is going to be disturbed and some of data is going to be lost. It's a one condition. Another condition for packet loss is that A doesn't want to send a data at some point and B is going to be rest now, but once A wants to send a data to B but B is sleeping, so your data is going to be lost. So for that we have a two kind of solution. One is fixed slot. Fixed slot mean whenever you are not using the internet, but one of a slot is always assigned from A to B, because A always want that B is not going to be sleep. So for that A always send one slot to the B. Or another is interleaving, is the same again. So this packet loss or FEC, it's mostly it happen in a VSAT communication, or whenever you are assigning internet to some of the organization, and organization is going to be closed at 4 p.m. So after 4 p.m. that internet is going to assign to someone else. So whenever somebody is online from the organization, so he needs a internet, so always one of some slide is always assigning to the organization. So the packet loss is the problem. The solution was assigning some slot to the customer. So the problem was limited bandwidth. So for limited bandwidth we can do a couple of things. The first, making a signal to be digitalized. So let's see, we have a audio signal. If this, let's think about this audio signal is analog now. So what we can do, you are going to convert analog to digital. So this is just a way how we can, like for example, we have X number of a sample in every second, like we see like 5 samples in 1 second. So this X means number of a sample. So we are going to digitalize the signal. So what mean by digitalization? Digitalization means you are going to convert each sample in a finite number of value. Finite number of value mean it may be 1 2 3 4 5 6 7 8 9, this kind of it, which is a whole number, rounded number, not be like 1.1 1.2. it's not to be like in a point, it always be like a finite number 1 2 3 4 5 6 up to so on. So this is called digitalization. And if you have a video, so one thing, audio signal have a samples in a video signal, each have a pixel, and pixel has a color, and each color has a value of bits, value of digital bits, digital signal. So for audio we have a sample, for a video, in a video all sample is there as well, but also have a pixel, colors, etc. So now the problem was limited bandwidth, so we need a compression for that. Solution is compression. So you are doing a compression now. So for a compression for audio signal, we have a audio signal, like we have a CD quality which have a 44,100 sample per second with the 16 bit per sample. So how many sample per sample we have? So how many bits we have? A 16 bits per sample. So when 16 bit per sample, it means that 44,100 sample multiply with the 16 bit, because one sample have a 16, so 44 to 100 sample will have multiply with 2. We are using stereo sound. Stereo sound mean like have a 2 channel, that's why we are using 2. If you are using some other kind of a sound or using 1 channel, so no need to write 2, just multiply bits with the sample. So when you are multiply this value, this one you have a value of this, which is 1.411 megabit per second. How it converted? Because you multiplied bits with the sample. So bits with the sample, it going to be bits, and how many bit per second? So this is called per second. Per mean is dividing. So let's see, now we have a 1.411 megabit per second, 1 second. Now for a 3 minute, now for a 3 minute song, so we have the value of 1.441, and 3 minute which have 1 minute have a 60 seconds, so multiply 60 second with the 3 which have a 180 second, so multiply 180 with this one, which is equal to 244 megabit per second. When you go to megabit per second, so we are going to be compress this data. So how you are going to compress? You are converting megabit per second to megabyte, and you know 1 byte is equal to 8 bit. So divide 254 by 8 and we will have a compressed data. So this is our compressed data. This was for a audio signal. Now coming to for a video. For a video, just again the same is we have a 320 and same like a pixel and color image with 24 bits. So this multiply with this one, all is multiplying, so the result will be 230 kilobyte per image. So again coming to 15 frame per second, multiply this with the 15, the same calculation as we saw before, the result will be this one. For 3 minutes of a video, 3.4 multiply with this one. So the video is just like we have a pixel and color multiply with the bits. So image have a 24 bit, just similar for a color, so multiply, so result will be in a kilobyte. You can be writing a bit as well, you can be writing a byte. If you are writing in a byte, so multiply with 8, or so if you want to write 230 in a way of bits, so multiply with the 8. If you want the signal in a byte, so divide the signal by 8. So this is the way how you can compress the data. So now coming to the audio compression, so we have a several technique for the audio compression. Like for the first one, like you can see here, like a GSM, the audio signal is like 16 kbps, and we want to compress GSM signal into in the code of G.729, which is used for voice or IP. So the 13 kbps is going to compress up to 8 kbps now. And also another code we use in for a voice or IP as well, which is going to compress your signal from 6.4 or 5.3 kbps. So in audio we have a multiple technique. The first technique was this one, which compress your audio signal. The second is this one. Now like you have a MPEG signal, which is known as by MP3 signal, MP3 video or audio. So the typical rate for the MPEG is 96, 128 and 60 kbps. The quality, so 96, 128 is depend on the quality of a signal. If you want a good quality, so you need to be work on 160. If you want a medium, 128. You want a lesser, so 96 kbps. So very little sound degradation. The sound is going to be a little bit disturbed, like disturb, not disturb. The sound is going to be buffer, like you can hear the sound, but up to some extent there will be some error kind of disturbance in the sound. If a file is broken up, each file is still playable. So it's a complex, like making redundancy reduction, etc. When you are making a 3-minute song, and in 3-minute song you are working on the 128 kbps, so you need to convert the 3-minute song into compressed form. So 128, you have 128 kbps, so 128 3-minute multiply 6 with 3 minutes is going to be 180. So it's equal to 128 multiply 180, it's equal to 23,040. So it's like a kilobits per second now, but we want to compress this data into bytes, so divide this value by 8, because I told you before 1 byte is equal to 8 bit. So this will equal to 2880 kilobyte now. So we want it in a mega, so point will come to this value, so it will be 2.8. so it's a kilo, again it's make a kilo, which is equal to 6 and equal to megabyte. So this is the way how you can compress your signal. So another technique for like a JPEG signal or JPEG audio or video you have, so divide the JPEG digitized image into 8 multiply 8 pixel block. So each pixel block or transform into frequency block using discrete cosine transform, and we will know this by FFT, first Fourier transform, and you study that in your differential equation book as well, or in calculus as well. The quantization phase limit the precision of a frequency coefficient. Quantization, I told you before, quantization means you can fix your number like 1 2 3 4 5 6 7 and so on, making a round number, and the encoding phase picks this information in a dense fashion. So now you can see one of the example, JPEG compression. So now you have a video or an image, some kind of a thing. So the first thing was divide your image into 8 cross 8 pixel. Then what can do next? So you can make a discrete cosine transform, which is also known as by FFT, first Fourier transform. Then you what you will do, then we will make the value into quantized form. Again the same thing, quantized mean 1 2 3 4 5 6. What does it mean? Maybe you can say that 2 pixel is equal to 1 value, so I mean 2 numbers going to convert to 1 value, so it's going to be compressed now. Then here you have a quantized table, which is going to be like 2 frame is equal to 1 or 4 frame is equal to 1. It's just like that. It's just like up to design, how he going to design. Then this quantization signal coming to the encoding phase. Encoding phase means some kind of extra thing is going to be added with the signal, because we want to be a secure signal and correct signal. So also have a some coding tables. So this is the way how we are going to compress JPEG audio or a video. So this is the way of JPEG compression. So video compression, like we have again a popular technique for a video compression again, like mpeg1 is used for cd-rom quality and which have a 1.5 megabit per second. mpeg is used for a high quality dvd and use 3 to 6 megabit per second, and mpeg4 is used for object oriented video compression. So now coming to the video compression of mpeg signal. So mpeg use interframe encoding, because now you are making encoding with the signal and going to compress. So we have three frames type. In a mpeg we have a three frame like I, B, P, and you can see how like I, B, P. So I frame is independent encoding of the frame, like a JPEG. There will be no encoding. You have just a signal without any encoding. So P frame encode difference relative to the I frame. So P frame have some encoding technique or have encoding stream in a P frame. So then we have a B frame encodes different relative to the interpolated frame. So again we have some different kind of encodes techniques here as well. Like you can see here, for I we will have a GP signal without any encoding. It's independent of encoding. It will have encoding, again encoding, have encoding, and so on. I again independent of encoding. So one thing which need to be keep in mind, no date frame will have a different size. Every frame will have a different size, so you will manage all different sides of a frame in a mpeg signal when you are going to compress the video. Then coming to complex encoding. So complex encoding mean motion of a pixel block when you are watching a movie. So there will be a pixel which is going to be change because screen is there, scenes changes, etc. So one thing, decoding is easier than encoding. Yeah, it's true. Decoding is too much easier than encoding. mpeg is used fixed rate encoding. So you are seeing this frame, which is the example of mpeg signal, which have I frame, B frame, and P frame. Now coming to the example of mpeg compression. Now you can see you have a two image, this one and previous frame and current frame. So previous frame mean we always have one of a reference frame, because you are going to compare new frame with the reference frame. So what kind of changes we did, so it means, so now you can see this example. So now we can see the example of mpeg system streaming, how the mpeg system is working or streaming, or we are seeing the mpeg video. So combine mpeg audio and video stream in a single synchronized frame. Like you can see this frame, this is a single synchronized frame now. So in this frame we are going to combine audio and video together. So the another is consists of hierarchy with metadata at every level describing the data. So each and every point is showing the data of audio, video, picture, etc. System will contain synchronized information. This is very important in all kind of multimedia application and technology. That audio, video and color, all these things need to be synchronized with each other. When somebody is showing the picture of a flower, so the sound is need to be say flower. It's not to be like that, that there is a picture of a flower and the previous one there was another picture. You are seeing, you are watching a flower, but he say there is a picture of a cat, so it means it is not synchronized. So always remember, you need to synchronize audio video with the colors. So now you can see the example. We have a PEG 1 and PEG 2 which have a PEG header, always have a PEG header, and a data system header, audio video and so on. And a PEG 2 is again same PEG header. We have already one system header, so no need to add, because when you are going to transmit simultaneously, so you are just using a one time system header, video audio video and video. So this is the screen how MPEG signal is transmitting or how we are watching a MPEG video. So this is the way you can see the images synchronized with the audio and video. You can also see this kind of example as well. You can make a group of a picture. This is your group of a picture. So group of picture mean one by one, and also make it in the shape of slice. So in a slice mean it will be one by one, not to be like in a disturbed order. So it will be in order form, that always you can see one by one image with the audio signal, because in audio signal I told you it need to be synchronized with the images or with the video. So now the problem is packet jitter. Packet jitter means variation and delay. So now you can see this one. You have a sender and receiver. Sender is there is no jitter, but in receiver is a jitter. What does it mean? You are sending this data 6543121, but you are receiving what 56. So it means there is a variation, there is a delay, there is disturbance, there is no synchronization between the data. So that's why you are receiving 5 first, then 6, then 4, then 3, and then 2, and then 1. So it means there is a jitter now. So that's why we also say if there is a jitter, so what we can do, we can remove the jitter and make the synchronize. So let's just see this example. We have a clock and we have a car. So you say that in a 2 second after 2 seconds your car need to be here. So after 2 seconds if your car is here, it means synchronized. But if after 2 seconds your car is not in a point B, maybe your car will be in point A, so the system is not synchronized. This is called jitter. So we always try to remove the jitter from the video because of delay. So now dealing with the packet jitter. So what does it mean and how we can treat the packet jitter? As I told you before, we will work on voice over IP, like phone over IP. How does phone over IP application limit the effect of a jitter? So what we can, a sequence number is added to the each packet. Let's see, this is your generated packet now. So we will be add some packets. So a timestamp is added to the each packet. Timestamp you need, so 10 frame will be received or will be sent after every 1 second. It's just like a time stamp of this one. So dealing with the packet jitter, like we have packet generated. This is your original packet generated now, and which is going to be sent. So after some time, I told you the timestamp is added with the each packet. So this signal is going to be received now. So packet received up to this extent, it's okay, it's fine, but after that there is a data loss. Now there is a data loss means there is a jitter now. So what we can do, we will add some play out schedule. We will reduce this jitter, and we have this formula how we can reduce the jitter, and we have a formula for speed and distance of signal as well. So now dealing with the packet jitter adaptive playout delay. So as you saw the graph before in slide number 13. So we had three different graphs. First was packet generated, the second was a packet received, and the third was a jitter, some data loss there. So for that we have a two different formula. The first one is delay and second is deviation. So di is stand for delay and deviation. Now you can u is just, for example, always take 0.0011. so ri was your packet receive instant, ti was your time, again vi your deviation. So now coming to this one, ti is the time stamp of the each packet. Each packet mean maybe packet number 1, 2, 3, 4, and maybe packet number nth. The time pkti is sent, so just mean like that. So ri is the time packet, I is receive, like pi is the time packet I is played, di is estimated average network delay, so vi is the average deviation of the delay. So putting the values of from a graph like packet 1, so you will see how much will be the delay and how much will be the deviation of delay. Deviation was the third graph. This is was like your deviation. So how much will be deviation you can see from this graph. So this was the formula for the jitter adaptive playout. So now we can see when we are facing a packet loss, so recovering from packet loss we have a technique, so the forward error correction technique, and you studied it in your data communication, data correction and data detection, like error correction and error detection. Like you saw the CRC, Hamming distance, this was the different technique. So Hamming distance was a technique which is going to correct the error, single bit error. So whenever there is a kind of error, so send redundant encoding chunk every n chunk, like you are going to exclusive or with the original signal. Maybe you studied in data communication and in a Hamming distance. If you remember Hamming distance concept, in Hamming distance we always do exclusive OR of the received signal with the sender signal or transmitter signal. So if one packet in this group loss, so we can construct, and I told you before, if there is a 1 bit error, so we can correct the error, but if it's more than 1 bit error, so Hamming this is not going to be corrected, so cannot recover, is greater than 1 packet. So what was the disadvantage is the smaller the group size, the larger the overhead, and so on. So now we can see the example in the image. So this is your original signal or original stream. So one is going to be transmit now. Okay, one is going to be transmit, so it is transmit. So it's say okay, I send the data 1. So because now this is synchronized now, so it's I send. So now this is next is 2. Okay, now you can send 2. So 2 is going to be sent. 1 is here. Okay, 1 is already received, so no need to receive the 1 again. So 2 will be here. So it's synchronized, and there is a comparison that the previous one is received or not. So now 2 is received. Now coming to this one, 3, 2 is 2 already sent it. So now 3 is coming here. So there is a error now. So when there is error, okay, forget about now this one. So 3 is going to be this one. Now it's next is 4. 4 is going to be transmit. 4 is going to be transmit. 4 is coming to here, and this 4 is now looking that, yeah, is 3 is there or not. So you say no, 3 is not there. Okay, now you can go fast. So 3 will be coming here. This is called error correction. Then 4 will be here. So this is your recover signal now, because you saw that 1 bit error. This was your bit error. Single bit error is recoverable in a Hamming distance. So now coming to the interleaving. So I divide 20 millisecond of audio data into small version of 5 millisecond each, and it's up to you. Packet loss upon have a set. So now this is the very good example of reconstructing the error signal. So we have a 4 block, 1 2 1 2 3 and 4. So we have a 4 block, and each block have a 4 number. So, and the upper one is, this one is your original stream. So this original stream is going to transmit now. Now you are transmitting from point A to point B. So this 4 block is transmitting now. So how we can manage now, what kind of technique we are going to use here. So this is block 1 2 3 4. So in a block 1, position 1 is used for a block 1, position 2 is used for a block 2, position 3 is used for a block 3, position 4 is used for a block 4. So position 1 is used for block 1, so 1 is here. So again, second block, number of a second block will be in a position 2, number of a third block in position 3, number of a block 4 in a position 4th. Then again here you can see this this block, the position of a block 1 is position 1, second block in a position 2, third block in position 3, fourth block in position 4th. So now coming to this block, block 1 in position 1, block 2 in position 2, block 3 in position 3, block 4 in position 4. Now come to this one, block 1 in position 1, block 2 in position 2, block 3 in position 3, block 4 in position 4. So now this is our interleave stream. We marked it now. So now this interleave stream is in this portion. Now it is moving. So we have this value now, 1 5 9 13, 1 5 9 13, then we have 2 6 10 14, and also now this data is corrupted now. So now how we are going to correct this data? So this is a corrupted data, and this is our another one. So this data is transmitting which have a error now. So again the same concept, block 1, block 2, block 3 and block 4. So position 1 is block 1, position 2 is for block 2, position 3 is for block 3, which have a corrupted data now, and block position 4 is block 4. Again position 1 is for block 1, position 2 is for block 2, position 3 is for block 3, position 4 is block 4, and again this one, position 1 for block 1, position 2 for block 2, position 3 for block 3, position 4 for block 1, position 1 for block 1, position 2 for block 2, position 3 for block 3, and position 4 for block 1. So now you can see we have one bit or frame is corrupted. So now how we are going to correct this corrupted data? So coming to the previous slide, this was the previous slide. So now this concept will be applicable. which is going to transmit, which is have a error, corrupted error. So at the end you will have a reconstructed. So this is reconstructed stream, and you know which is corruptible, so you can easily find a corrupted signal. So the receiver based repair, so it's simple. The simplest form is packet repetition. Then the replaces lost packet with the copies of the packet that arrived immediately before the loss. So it is like the same as we saw in a interleaving. So when the data is going to be corrupt, so the method of interleaving is going to be used there for reduce the packet loss. So that was your second lecture. So you need to be concentrate on a solution, how we are going to be reduce a delay, how we are going to be compress the data, how we are going to be reduce or correct the packet loss or error correction. So if you guys find any question, so in the next lecture you guys can ask, and I will be here with you, so and I will be answer that. So